Gas laws examine the effects that pressure, volume, and temperature have on the behavior of gases. Today, I'll be working on 4 gas law problems step by step. To start off, a sample of helium gas occupies 57.9 liters at 300 kelvins and 1 atm. What is the volume of the sample at 423 kelvins and 1 atm? Since pressure, volume, and temperature are given, we can use a combined gas law. Going back to the problem, fill in the values for the original pressure, volume, and temperature, as well as the values for the new pressure, volume, and temperature. I've shown you the values below. All we need to calculate now is the final volume. Since the original pressure and the final pressure are the same at 1 atm, we can solve the problem using Charles's law. I set the equation in terms of the new volume. Now, the new volume is equal to the original volume times the new temperature divided by the original temperature. If we plug in our values into the equation, that gives us 57.9 liters times 423 kelvins divided by 300 kelvins, and that gives us 81.6 liters. For our second problem, what is the pressure in millimeters of mercury in a 12.2 liter vessel that contains 2.34 grams of carbon dioxide, 1.73 grams of sulfur dioxide, and 3.33 grams of argon at 42 degrees Celsius? Because we're given more than one type of gas, we can use the equation PV equals nRT. However, N stands for number of moles. We have all these gases in grams, so we need to convert them to moles. I've shown you the calculations below. That gives us 0.0532 moles of CO2, 0.0270 moles of SO2, and 0.0834 moles of argon. We'll add them all to get the total moles of gas, which gives us 0.164 total moles. Now we have the answer in atm, but we need to convert it to millimeters of mercury. So I've multiplied 0.347 atm times 760 millimeters of mercury for every 1 atm. Our answer should be 264 millimeters of mercury. Okay, for problem number 3. At 333 Kelvin, which of the pairs of gases below would have the most nearly identical rates of effusion? Rates of effusion refers to how fast a gas escapes through a small hole in its container. So, gases that have similar molar masses will also have similar rates of effusion. Now we have to calculate the molar masses of each of the compounds. I rounded to the nearest hundredth for simplicity. So as you can see, the gases carbon monoxide and nitrogen have identical masses at 28.01 grams per mole. So our answer will be B. For our last problem, a sample of helium gas at 5.6 atm and 25 degrees Celsius was combined with 4.5 liters of neon gas at 3.6 atm and 25 degrees Celsius at constant temperature in a 9-liter flask. What was the total pressure in the flask, assuming the initial pressure in the flask was 0 atm? Since we're dealing with more than one gas again, we can use PV equals nRT. We need to find the moles of each gas. For helium, we're given a volume of 3 liters. I converted 25 degrees Celsius to 298 kelvins, and we also have a pressure of 5.6 atm. So to solve for the number of moles, I rearranged the equation to make N equal PV over RT. By plugging in the values, you should get 0.687 moles of helium. So now we'll do the same with neon. This time, we have a volume of 4.5 liters and a pressure of 3.6 atm. The temperature remains constant. The equation remains the same, so we should get the value of 0.662 moles of neon. So now we can calculate pressure using our total values. The volume of the flask is 9 liters. We'll add moles of helium to moles of neon to get 1.35 total moles of gas. The temperature remains constant. I rearranged the equation to solve for pressure, so P equals nRT over V. That gives us 1.35 atm times our gas constant times 298 kelvins, the whole thing divided by 9 liters. So that should get us 3.67 atm.